Hi everyone, welcome back to CHM421. In this video, we will continue our topic 4, Titrimetric analysis. I specifically on acid-base titration. So in this video, we will focus on the back titration. So what is back titration? Back titration is a titration method where the concentration of analyte is determined by reacting it with known amount of excess region. The remaining excess region is then titrated with another second region. So the keywords for back titration is excess region, and they have a second titration by using another second region. Again, big titration is a titration method where the concentration of analyte is determined by reacting it with known amount of excess region. The remaining excess region is then titrated again with another second region. So, back titration is the process in which the excess of standard solution used to consume an analyte is determined by titration with a second standard solution. As I said just now, this back titration is a double titration. The first titration, we add on excess amount of standard solution. Why standard solution? Because we know the concentration. And then the excess amount of solution will be undergo a second titration by using another second standard solution. Meaning that in analytical chemistry, titration can be done either direct titration or back titration. So in direct titration, standard titrant is added to the analyte until it reached the end point. Remember, in the titration, we have two important points, equivalent point and also end point. So direct titration, we do the titration using the standard solution until we obtain the end point. What is back titration? Is I explained just now. Back titration is a double titration. First titration we add excess amount of standard solution, and then the excess amount of standard solution will undergo a second titration with using another second standard solution. So in back titration, non-excess standard region or standard solution is added to the solution, and the excess will be titrated during the second titration. So I hope you can differentiate what is a direct titration, what is back titration. Okay, this is the reason why sometimes we need back titration. So, because the main reason is the direct titration, single titration, maybe the direct titration for analyte of the reagent maybe is not feasible. This is due to several reasons. The common reasons is listed here. Maybe the reaction rate is low, or we cannot obtain a suitable indicator that can be used in the direct titration, or the color change if the endpoint is slow, or in other words delay, or we cannot observe the color change sharp, and maybe the during the direct titration the endpoint is far from the equivalent point, or another reason the standard solution is lack of stability. So this is all the reason that need us to perform the back titration. Reaction rate slow, indicator, no suitable indicator for the direct titration. The color change at the endpoint very slow. The endpoint very far from the equivalent point, and the standard solution not stable. So this is the reason we perform the back titration. Remember, back titration is double titration. The first titration we add on excess in an excess amount of standard solution, and then we titrate. We continue with second titration by using another standard solution. So this is the example of back titration. The titration of insoluble organic acid with sodium hydroxide is not critical because of the reaction is slow. So for this particular chemical reaction, it said the reaction is slow. Because of the reaction is slow, so we need back titration. To overcome it, sodium hydroxide and axis, because this is the standard solution. Since the reaction is slow, we need back titration. So during the first titration, we have to adding sodium hydroxide and axis. Okay, so the keyword is should be axis, and allow the reaction to reach the completion, and then follow by titrate the excess sodium hydroxide with a standard solution of hydrochloric acid. So as you can see here, the first standard solution, which is sodium hydroxide, will undergo a second titration by using another standard solution, which is Cl. So this excess sodium hydroxide is a strong base. This one is a strong acid. Okay. So this is the chemical equation for the second titration. During the back titration, sodium hydroxide reacted with hydrogen chloride to form sodium chloride and water. So if you confused about this chemical equation, you can split these chemicals to Na plus, OH minus, H plus, Cl minus. So the positive sodium will be reacting with chloride, and hydroxide will be reacted with hydrogen, to form sodium will be reacted with chlorine ion to form sodium chloride. Hydroxide will be reacted with hydrogen to form water. So the system has gone from being acid past the equivalent point to the basic uh, basic side in the excess base, because you have to remember this one sodium hydroxide in excess. So the system has gone from acid past the equivalent point to basic, and then back to the equivalent point. The final titration to the equivalent point, we call it back titration. All right. So as you can see here, is a double titration. This is the first titration. This is the second titration. During the first titration, the sodium standard solution of sodium hydroxide is in excess amount. And then during the second titration, the excess amount of sodium hydroxide will be titrated again with another standard solution of HCl. All right. So here is some example calculation related to back titration. I think we can do it together. We try. Uh, 150 ml of 0.2105 molarity of nitric acid HNO3 was added to the excess in excess to 1.3415 gram of calcium carbonate, meaning that this nitric acid we add in excess amount. The excess acid was back titrated. It's mentioned here. Back, back titrated, back titration with 0.1055 molarity of sodium hydroxide. It required 75.5 ml of the base to reach the equivalent point. So this one is strong acid. This one is a strong base. All right. So the first question is name the suitable indicator used in above titration. Since this one is titration between uh, strong acid with strong base, the equivalent point pH 7. So normally the indicator that we can use are either uh, phenolphthalein or metal orange. So the phenolphthalein normally in purple, metal orange in orange color. So you can suggest one of the indicator, either you want to use phenolphthalein or you want to use the metal orange. So the second question is asking you about, the first question is indicator. The second question is asking you about draw the titration curve for the above titration. Okay, so which the things that we added during the first titration, this one added, meaning that is a titrant in the biurate. In the second titration, sodium hydroxide is added, is titrant. Okay, so because this is a back titration, remember this is a back titration. Our back titration in this situation is a strong acid and strong base. So the equivalent point, it should be pH 7, if you still remember. So yeah, so because the back titration just now is strong acid, strong base, meaning that the titrant is sodium hydroxide, and then the excess standard solution from the first titration is hydrochloric acid in the excess amount. Okay, it's not hydrochloric acid, it's the nitric acid. So remember, we will add the sodium hydroxide slowly. So in the titration curve, of course, the y-axis pH, and the x-axis is the x-axis is whatever titrant x is titrant in biurate, y is pH. So the titrant in biurate that we use in this case is volume of sodium hydroxide. So it's a sodium hydroxide. So it should be, you can see, you can write it here, sodium hydroxide added in milliliter. So you can name the x-axis either volume of sodium hydroxide or volume sodium hydroxide added in milliliter. All right. So you know several information from the question. Since the reaction is a standard strong acid, strong base, so meaning that the equivalent point pH 7. This why we draw pH 7 equivalent point here. So the question is why the curve is in this way? Why not in this way? Okay, my question is, Why the answer give you the curve in this way? Why not in this way? Okay, so you have to visualize what happened in here when we add on sodium hydroxide. Of course, this is nitric acid is a strong acid. Before we add 1 drop of sodium hydroxide, so the pH it should be in the acidic pH. This is why we start with lower pH, because this is the pH of uh, acid. This is the pH of base. So in the beginning is nitric acid. So the pH it should be in the uh, acidic range. So meaning that when we add on more and more sodium hydroxide, the pH inside will be changed from acid into basic. This is why upon increasing the sodium hydroxide, you will observe increasing the volume. Upon increasing the volume, the pH will be increased into the base region, because it will neutralize. These two will be neutralized to each other. Okay, so this is the reason why our curve like this, not like this. Okay, it's a very determined by the what is the analyte in the uh, conical flask. Okay, so for this a strong acid is strong base, the equivalent point pH 7. Alright, so this is the titration curve. Okay, moving forward to another question. Calculate the percentage weight per weight. Is asking you the percentage uh, is asking you the percentage of weight per weight of calcium carbonate in the sample. So meaning that calcium carbonate in the sample. So the sample is 1.34514 gram, 1.3415 gram. So you have to calculate what is the amount of calcium, the real calcium carbonate in the sample after you perform the titration. So this one times 100, and then you can get the answer. So the problem now, you have to determine what is the real amount of analyte, which is calcium carbonate in the 1.34.5 sample. Okay, so this is the initial amount of calcium carbonate. Okay, sorry. I think I just lost my internet connection just now. Okay, let's continue. Now, the question is calculate the percentage weight per weight of calcium carbonate in the sample. Is I said just now, you have to determine what is the real amount of calcium carbonate in the sample by using the titration. In this case, we do double titration, direct titration, and back titration. Okay, how to do it? So the first, of course, you should know the chemical reaction. The first titration is between nitric acid, which is in excess amount, reacted with calcium carbonate to produce calcium nitrate, CO2, and also H2O. So you have to balance this chemical equation. So just do as I did just now. Uh, Nitric acid can be dissociated into H plus NO3 minus calcium carbonate to plus carbonate to minus. And then you just react the uh, calcium with nitrate, positive with negative. And in this case, the the product is uh, calcium nitrate plus carbonate will be produced as CO2, and H will be produced water. So you have to balance the equation. Okay, so you have to do the equation balancing. Because the water is H2O, so we need two water, we need two hydrogen at the reactant side. This is why we multiplied by 2. So two hydrogen, NO2 is already 2, calcium okay, carbonate CO2. So another one oxygen in water. So this one is balanced. All right. So the second equation, the second chemical equation for back titration. So the excess nitric acid reacted with sodium hydroxide. So you can label this one. Sodium hydroxide is a strong base. Nitric acid is strong acid. So again, you can dissociate like this in order to know what is the product produced from the reaction. Okay, so first we have to know the mole of uh, acid in the first titration. Okay, we have to know the mole of this acid. Because We want to know at the end of the calculation, we want to know how many grams of this chemical. So in order to know gram, you should know mole. Where you can get mole, either mole from molarity or mole from reaction. Okay, so here we know this nitric acid will be reacted by with this calcium carbonate. So when we know this mole, we can calculate this mole. But the problem now, this mole is in excess amount. So we don't want the excess amount, we want the limiting mole. We don't want the excess mole because the mole that determine the product is a limiting mole, it's not excess mole. So in order to determine the limiting, this is why we have to perform the back titration. Okay, so from the first equation, we know 2 mole of nitric acid, this one, 2 mole of nitric acid reacted with 1 mole of sodium, 1 mole of calcium carbonate. So this is the relationship. Okay, this is the relationship. So we have to determine the mole of nitric acid. So way to define, how to calculate the mole. Of course, as I said at the beginning, mole can be from mass over molar mass, or the mole can be calculated from the molarity, mole per liter. So it's depending what kind of information given in the question. So if you back to the question, you are given 150 ml and 0.1205 molar of nitric acid. So from this information, you can calculate what is the mole excess of the nitric acid. Right, 150, 0.12. Okay, so we know this excess amount of nitric acid 150 ml. So you can write it here 150 ml, and then with 0.1205 molar. Okay. So as I mentioned just now, you have to calculate the mole of nitric acid in excess. But we cannot use this mole in order to calculate the mole of calcium carbonate because it appears in an excess amount. So we have to determine what is the limiting mole. How to determine the limiting mole? This is why we perform the back titration. Okay, so now we settle this first. Calculate the mole excess of the acid nitrate. As I said, you can calculate from here or from molarity. It's depending on the information. Now we are given the molarity. So in order to calculate the mole, the molarity has to multiply by volume of solution. So mole is molarity 0.1205 times volume 0.15 liter. Okay, because why this is in a liter, given in milliliter, we have to change it into liter because the unit of molarity is mole per liter. So later on, we have to cancel the unit in order to get the mole. Okay, so 150 ml divided by 1000. So you get 0.15 liter. So calculate 0.2105 times 0.150. So you can obtain 0.031575, or you can use the index. So you can write or 0.03158 mole. Okay, okay, mole. So now this is the mole of excess nitric acid. But we don't want this. We want to calculate the limiting mole in order to obtain the calcium carbonate. All right. So as I said, in order to do the limiting, we have to do the back titration. So the back titration, this is the chemical of back titration. After we balance the chemical equation, we know 1 mole of nitric acid will be reacted with 1 mole of sodium hydroxide. 1 mole and also 1 mole. So you can write here, back titration is to determine the limiting mole. So uh, so we know, okay, the relationship is 1 mole nitric. The relationship is 1 mole of nitric acid with 1 mole of sodium hydroxide. So we know mole of excess is 0. Okay. As we understand during the big titration, this excess nitric will be titrated with sodium hydroxide. So you can imagine it here. You can, so on the top is sodium hydroxide. It the flower is HNO3 excess. Okay, so it said in the question, the excess acid with was back titrated with 0.155 molar of sodium hydroxide. It required 75.5 milliliter to reach the end point. So it needs 75.5 ml. So you can write it here. Sodium hydroxide required 75.5 ml, 75.5 ml with the molarity of 0.1055. 0.1055. So we can calculate the mole of uh, this one is wrong. We calculate the mole of sodium hydroxide. So the mole of sodium hydroxide is 0. Using the formula of molarity, 0.1055 molar times 75 milliliter converted to liter, 0.0755. 75.5 divided by 1000, 0.077, and then you times you 0.1055 times 0.0755. So you obtain 0.000. So this one is 0.007965 mole. Okay, 65 mole of what? Mole of NaOH. So now we know the we know the relationship between mole of nitric acid and mole of sodium hydroxide in the back titration is 1 to 1. So it meaning that this mole is similar to 0.00965 mole of what? Nitric acid. So this is limiting. It's not limiting. This is the mole react with sodium hydroxide during the big titration. So now we have to calculate the limiting mole. This is the mole of limiting. So in order to calculate the limiting mole, the mole of excess the okay, the mole of nitric acid in excess minus with the real mole reacted in the titration. This why uh, this mole, excess mole of nitric acid 0.058 mole minus the real mole during the titration 0.007965. So you can get 0.01185 minus 0.007965 mole. So you can obtain 0.2 0.023615 mole. Okay, of what? Of HNO3. So this one is limiting. So when you know the limiting mole of nitric acid, so you can use this back to the first formula, the first equation, you know 2 mole of nitric acid will be reacted with 1 mole of calcium carbonate. So you can determine the mole number of calcium carbonate. So this is the relationship: 2 mole of nitric reacted with 1 mole of calcium carbonate. So the real nitric acid required for the reaction is 0.02365. So this one 0.023123615. Okay, so you can determine the mole of calcium carbonate. So the mole of calcium carbonate, this one is X. So in order to determine the X, this 0.0236515 multiplied by 1 divided by 2. Okay, so you can say X 0.02365 multiplied by 1 divided by 2, so you can obtain the mole number of calcium carbonate. 0.02365 times 1 divided by 2. So 0.011 8075 mole. This one is mole of what? Mole of calcium carbonate. Okay, so from the mole, of course, when you know the mole, you can calculate the mass, because you know mole is mass over molar mass, and then mass is mole times molar mass. You can use the periodic table. So I just use whatever given here is 100 gram per mole. It's 100 gram per mole. This one is a mole. So you can cancel the mole in the mole. You can obtain answer times 100, 1.18. How many gram? 1.1875 gram. Okay, so when you know the gram, this now you already know the gram. Gram of what? Gram of calcium, the real calcium carbonate. So in order to calculate the percentage of calcium carbonate with per weight, so the real one that you determine by using the titration divided the amount of sample 1.3415. 1.3415 gram, and then times 100, you can 1.18075 divided 1.3415 times 100. So 88.0. 0 1 0 2. Okay, so this answer is slightly different because it's a contribution of the decimal point, but it's still acceptable. Okay, 88, 88. All right, we done this question. Another question. Okay, maybe you can try this. It's quite similar. It's quite similar. Uh, because it's quite similar. Uh, the sulfur content of a steel. So sulfur and steel determined by converting it to H2 gas, meaning that we have a steel sample and then we want determine the sulfur. So the sulfur in the steel converted into H2S. The H2S didn't absorb using 10 ml of 0.005 molarity of iodine. Okay, and then we said here back titration is done to react the axis I. Okay, so meaning that the first titration is iodine is a standard solution and axis, and then you have in the aluminium flask you have H2S. Okay, and then we perform the back titration by react the excess of iodine with 0.002 molarity of sodium S2O3. So this is the second titration. Sodium S2O3. So in the aluminium flask, I2 and excess amount. So if 2.06 ml of NO2 is required for the titration, so this one required 2.60 ml is required for the titration. How many milligram of sulfur in contain? So if this required, how many? Sorry, this is not hydrogen. This is sulfur. How many sulfur in the steel? So it's gram. So we have to determine this one. Okay. So before we start the calculation, just take note of the information given. The iodine excess in 10 ml 0.005 molarity, and then titrated with 0.002 molar sodium S2O3 if 2.6 required, and then how many gram. Of course, the strategy we have to calculate the mole of this one the mole from here, because the mole can give you a mass, so we have to calculate the mole between H2 and H2S, I2 and H2S, but we cannot use it directly because in excess. So we have to determine the real H2. So the real H2, uh, the mole of H2. So now from this mole, we can calculate this mole after we know the mole of the excess, mole of real, and then we minus with mole of excess, and then we can get the mole of the real H2, and then can relationship with hydrogen sulfide, and then we can get this one. That's the plan. Okay. So this chemical equation is already given in the question. Uh, it's quite easy because it's already given. It already balanced. So we just understand what is the relationship stoichiometry between reactant and reactant during do the calculation. Okay, it's the same with the previous question. First, we have to determine the mole of this iodine in excess. So the mole can be obtained from molarity. Okay, determine the mole. So determine the mole by using formula of molarity. Is a mole per liter. Okay, so initial mole iodine in the first titration, which is excess amount. Information is given. So 0.005 molar. This one is again mole per liter. This why you have to convert the 10 ml to liter. So 10 ml divided 1000 is 0.01, and then multiplied by 0.05. So you obtain your mole number 0. Mole of what? Iodine and excess. So this mole will be titrated. Oh no, this is the excess one. So the for the back titration, we know the back titration. We have to determine the mole of iodine. Okay. Let's say I just delete this one. Okay. So we have to determine the mole of. We have to determine mole of I2. We know I2, 1 mole of I2 reacted with 2 mole of this one. So we can calculate the mole of H2O3 because the information is given already. Mole of Na2C2O3 from the molarity and volume 0.02 molarity times volume 2.6, meaning that 2.6 divided by 1000, 0.0026 liter. And then you multiply 0.02, sorry, 02, you can obtain 0. You can obtain 0.00, how many zero? 150, 1424, 1, 2. Okay. So this is the mole of what? This is the mole of Na2CO3. So when you know the mole, because you already know the relationship from the chemical equation, 1 mole of iodide will reacted with 2 moles of uh, H2O3. Okay, so you can calculate the mole of I2, and the mole of I2 is uh, mole of I2 is yeah. If you confused, you can write it here. You want to determine the amount of this. You want to determine the mole of I2, and then you already obtain 0.0000005 mole. Uh, mole S2 or 3. So in order to calculate the X, this is the X. So cross multiplication 0.0052 times 1 divided by 2. Okay, so yeah, I just write it here. I just try 0.0000005 or 2. 2 times 1 divided by 2. Okay, so answers 0.000052 times 1 divided by 2. 0. What? 0.0000026 mole of I2. Okay, so the mole in excess just now, this one should be deducted with the mole H2 from the back titration. So you can obtain the mole of real iodine. Okay, so initial is 0. This one it should be 0.005 from the initial. Okay, and then minus 0.0000026. So you can obtain 0.0049974 more. Okay, so the relationship between I2 with H2S is 1 to 1. So meaning that mole of H2 is equivalent to mole of H2S, because this one is 1:1, and then you can calculate the mole of S. So 32 is the molecular mass of sulfur. So 0.1599. So 0.1599 gram of sulfur. What's wrong? We double check. Ah, this one. This one is wrong. Oh my god. 0.0000. So you have to be very careful when you do the calculation. So 0.04. So answers times 32. 0.15. What's wrong? Millimole meaning that milli, 0.milli, 2, 3. Hmm. This one is correct. Okay. What's wrong with my calculation? This one, 3, 3, 1, 2, 1, 2, 3, 1, 2, 3. So this one also correct. I think 26. One. So it should be how many zero? 1, 2, 3, 4, 5. This one should be correct. So if you want to use 1, 2, 3. 1, 2, 3. Okay, that's so correct. So what's wrong? So 0.05 minus 0.0046, 0.0474 milli. If milli, meaning that if 0.0412, 1, 2, 3. So it should be 0.0474 milli, and then convert it into 1. Hold on, why so 1, 1, 2, 3, 1, 1, 1. So 2. Ah, hiya. Why? 0.000, 0.00049. Okay, so 0.0004974 insert times 32. 0. 0.0. Hopefully it's no more wrong. 0.01599.68. So if you want to do it in milli, what's wrong? 1, 2, 3, 50. Hey, the answer is like this: 0.474. But why I did this? Hmm. Why I get this? What's wrong? Oops. This look like correct. What's wrong with my calculation? 245. 245. Hmm. 1, 2, 3. So I think this is should be hmm, should be 4. Why I get the right 0.0005? So this one should be okay. Let's settle this 0.00005. It's 2 means 0. 240. 240. So 0.000049734 more, and then you have to correct this. Times 32. 4972 times 32, 0.0015. So I think I get the answers already. So it's a 0.00159,168 more. If I want to convert it to milli, 1.15, 1.159 milli more. Okay, I think uh, you can try and double check all the calculation. So I think this video is already too long. I will stop it here. We continue with another video to discuss a few example related to back titration. Okay, thank you again. You have to try. Make sure you double check all the numbers. All right, see you again on the next video. Okay, bye bye.